this RISIS Research Seminar series, which came to number 37, which shows the success of this series. You know the format. We have a presenter, we have a discussant, and then we have an open discussion. Today's topic is a typical combination of technologies in regional co-inventor networks. So we are moving to technology and to patenting, and to discuss an issue which resembles the same things we have in science, that combining knowledge from different areas can create more scientific advancement on one hand, and on the other hand, more innovative outcomes for the economy. So we have very competent presenter, Balázs Lengyel, I hope got it right, from the Center of Economic and Regional Studies in Budapest, and we have Lorenzo Cassi from University of Paris, Sorbonne, as a very competent discussant. The usual rules apply. Please mute your microphone. We like having your cameras open so that Balázs is not speaking just to a list of names, but to some faces. After the presentation, there will be a discussion. You can either directly intervene, opening your camera and your micro, or raise your hand, or if you wish, post your comments on the chat. With this, I would like to thank Georg and Rita for managing this seminar series, and give to Balázs the word for your talk. Thank you.
Well, thank you so much for the kind invitation. Let me start then the talk directly. My name is Balázs Lengyel. I'm an associate professor at Economie University and a senior research fellow at the Center for Economic and Regional Studies. So my central interest is collaboration networks and social networks in general, and I try to understand how these networks contribute to economic and technological progress in cities and regions. And today I'm going to present to you a paper that is already published, but hopefully that's only like the beginning of series of papers that we try to do in the field of regional innovation. So the idea is that the structure of structure of collaboration among inventors in a region can predict the success of technology combinations and novelty generation in regions, because these networks work as channels of knowledge flows that help knowledge sharing. So let me start with the general claim that is known to all of us, is basically that innovation concentrates in urban areas, because innovation needs diverse knowledge and agglomeration economies at play that help us to create novelty. So now I would like to concentrate more on the small world network phenomena that is really at play, how knowledge is shared on the globe and even in local realities, because we live in a small world network such that the access in this network is very short, even in large distances. So the number of steps on average that one has to take from one random individual to another random individual on Facebook is 4 globally, which has consequences on innovation and other economic phenomena as well. So for example, we know very well that disease is now spread very quickly across the globe. We know that very well from the COVID experience, but we also know that recent innovation spreads very quickly. Just think about generative AI, which was created recently. Now, basically, everybody's using that. So, starting from a wide perspective, just want to mention an example why networks matter and how network dynamics might matter. Because these small world networks not only explain how information spreads quickly, but can understand, like we can use that also to understand why still there are some inequalities and even growing inequalities across the globe and also within cities. So an answer for that is basically that even in small world networks, we see groups emerging. because in networks, similarity across nodes and triadic closure in the networks lead to emergent groups in which some characteristics describe the group. In this example, from US high schools, it's ethnic background that matters in these emergent groups. On global scale, it's more economic prosperity that matters in how and what type of network fragments emerge. And if network fragments are already there, then due to difficulties of diffusion across these polarized parts of the network, there might be some polarization, which can lead back to network fragmentation. So now of course, we are talking about innovation. So, but I think that this framework might also work for how we understand the role of networks, network dynamics for innovation, because in innovation networks, what matters is similar specialization in knowledge, which increases the probability that two individual inventors will collaborate. Now, because probably network closure is still at play, such that inventors tend to collaborate if they have a common collaborator, because probably they know each other with a higher likelihood. This will lead to fragmented networks in which increasing specialization is present. And this, like scholars have warned us very long ago, that such increasing specialization in networks can lead to local collaboration networks in which that might be too cohesive or locked into certain technologies, which can lead to a decreasing regional resilience against external shocks. Okay, so this is the general framework I would like to talk about. But we have to keep in mind that in such networks, in regional innovation networks, bridging across fragmented network partitions might be on purpose, because in regional innovation literature, we tend to think that inventors might outreach to external collaborators, to other regions, to get access to diverse knowledge, but it might also happen in the local context within regions if there is available knowledge which is different from mine, and it's beneficial to get access to that. The inventor might know about that benefit and use the opportunity to reach out to other specializations in the network. So this is the general framework I would like to talk about in detail. But before going into the paper, just a very short summary about small world networks. I think Hungary needs some marketing these days. And let me start with a novelist who kind of wrote about the potentials of small world networks early in the 1920s. So he thought that we might need very few steps on the globe to get to anybody through a friendship network, which basically was proven in the 60s by Stanley Milgram, a very famous social psychologist, who proved that indeed, despite that most of our networks around us are very cohesive because our friends tend to know each other, the average step that we have to take to get any other individual on the globe is very small. So in his the small world problem paper, he showed that the average step one has to take during a chain which was forwarding a mail from an individual to a target person was 6 in the US in the 60s. Then in the 90s, Duncan Watts and Stephen Strogatz came with a generalization of small world networks, saying that even though we have cohesive networks that we live in because our friends tend to know each other, there are only very few bridges needed across these network fragments that can make the network already very small, because these few number of edges make the connection, which speeds up diffusion and speeds up finding individuals in networks. So what does it mean for social sciences? It means that we live in cohesive networks, basically, in which people tend to know each other, and few bridges across these cohesive parts of networks establish very short paths that creates channels for noise sharing across different groups or information diffusion. In social sciences, widely speaking, in social networks, these align very well with the social capital literature. So these cohesive fragments of networks tend to think about as strong ties or cliques that help us to develop trust, mutual understanding, process complex information, versus the bridges or weak ties can provide us with diverse information. So now we understand, and I think that's a conclusive insight from the management and sociology literature, is that the combination of both the cohesive, the benefits of both from the cohesive parts of the network and from the bridges is needed to maximize success of creative projects or group dynamics and so on. So this is a regional innovation paper, and we are not the first one to talk about, of course, collaboration networks across co-located inventors. The first seminal paper I would like to refer to is by Lee Fleming and colleagues, who were the first to study small world network structure and regional innovation. And they found that even the formulation of the small world networks and the indicator that they used to measure small worldness of network was not correlating with future innovation success or the level of patenting. Short access, so the path length in the co-inventor network was correlated with the future levels of innovation or patenting, because, and the general claim is basically the same, that short access in such a network can speed up information flow and induces the combination of knowledge. So in this example, in this illustration, you see a co-inventor network from Silicon Valley, in which most of the cohesive collaborations are within companies. And cross-company collaborations establish basically the bridges that help the information and knowledge diffusion on the regional scale. There were many papers that followed and looked into the question how the structure of collaboration networks among inventors can help regional innovation performance. Some of them even found that the collaboration network is not helping regional innovation. Some of them looked into the structure within the region and the role of collaboration networks with other regions, and some of them also looked into how the structure of co-inventor networks is related to how much that region or city is specialized or diversified into certain technologies. Our contribution to this literature is basically on two fronts. First, we look at on radical innovation, but I will talk about how we measure that. So atypical combinations of technologies, basically combination of those technologies that have been rarely combined before the certain patent that came out, and that we can claim that's an atypical combination or new combination of technologies. And the second combination, which I think is basically has a lot of potential, and that's, I think, a very important niche, is basically what is the role of technological domains in this collaboration network, because still in these previous papers that I cite, it was still not understood how combination of knowledge happens in these networks, because we did not include information of how technologies and technological expertise were distributed in such a network. So what are we doing? We use European patent data that we collected from the PATStat database, and that includes the information on inventors, their location. So we use the NATS2 region of the home address of inventors, and of course we can extract information on technological classes that is included on each patent, and then we can quantify combination of such technological classes and patents. Let's talk about then the dependent variable and how we construct that, how we measure atypicality, which is a form of measuring radicalness. Of course, we cannot, so there might be other forms to identify whether a patent is a radical novelty. Now we simply measure a typical combination on each patent by measuring whether the IPC class I and J is combined on the certain patent, measuring the observed previous combinations of I and G compared to the expected combinations of I and G, given the sizes or number of patents in technologies I and J, and divided by the standard deviation of previous combinations. So if that z-score is below 0, then we can say that the that two technologies I and J have been combined before on a smaller scale than it would be expected given their size. So we can identify that technology combination on each patent as an atypical one. Previous papers, like the one by Lars Mewes in Economic Geography, showed that such patents that are atypical concentrate more in cities, in large cities, than those ones that do not classify as atypical patents. And we also see that some of these are more concentrated in typical patents. Some of the technologies, some of them are more concentrated in atypical patents. For example, patents in physics are more typical than atypical. So then what we do is basically we aggregate that information on the regional scale. So then, of course, regional size matters because probably atypical innovation, as I mentioned before, is concentrating in large cities. So what we want to do is that we want to disentangle that this measurement from regional size measures. So therefore, we calculate the share of atypical patents in the NATS2 EU regions to avoid the effect of urban scale. So that's going to be our dependent variable, and then we try to understand how that is correlating with the structure of inventor collaboration. So for that, what we can do is that, what other people have done before us, is that using the co-occurrence of inventors on patents, we can create a inventor collaboration network such that inventors A, B, C, D, and E are collaborating on patent one, so they will be linked in the co-inventor network, which is a straightforward way to deal with collaboration networks, but it generates problems. So one of the problems is that it automatically creates a cohesive part here, as you can see, because these 5 inventors are automatically connected, assuming that everybody knows everybody in this network. So to deal with this problem, we use a method that was recently introduced by Luciana Piquero and Jerome Vicente in Research Policy in 2019. And here that's an illustration from our case directly. So here what we assume is, and to just avoid this problem of automatic triad closure in such co-occurrence networks, is that we handle structurally equivalent inventors as one node in the network. What does it mean? It means that here A, C, and E inventors have the identical connections in such a network, because A is connected to C, E, B, and D, and C and E are connected to the identical set of nodes. So we form one node out of these 3 nodes and keep B and D separate from that node, and just assume that B and D has also observed that these 2 nodes have also identical sets of connections. So we merge B and D. So when we do that on a regional scale, you can see that some collaboration networks remain the same, because in the case of B, you have 3 inventors who are still connected, but have different sets of connections if we compare them within that component. But in the case of A, we merge these 6 nodes into a single node, because these inventors have identical connections. So we do this transformation before calculating our network measures. And now I choose the form of talking about the measurement first, and then about the hypothesis next, because yeah, that might help to formulate my points. So here we have to. So one thing we wanted to do is to compare the result with the result of Fleming and others in organization science. So therefore, the first network variable we quantified was on small word mass. So here, 2 indicators are needed to quantify whether a network is small word or not, or how much it is small word or how much it is not. The first part is quantifying the average path length, so the number of steps one has to take from any node to any other nodes in the network. So because and the other one is clustering, so how many triangles form in the network compared to all the possible triangles that might be formed on the network. So because we need to compare regions that are very different in terms of size and in terms of the network size, we need a null model for both of these measures that can make these regions comparable to one another. And these null models, in the case of clustering coefficient, the null model is a lattice in which the number of triangles is fixed. And in case of the path length, the null model is a random model in which the path length is usually very small. So we compare the path length that we observe in our regions to a random network, and the clustering coefficient to a lattice network that we formulate our small wordness indicator, which will scale from 0 to 1. Okay, so what do we expect from this indicator? We expect a reversed U-shape correlation with atypical combination. Why? Because as others said before, both type of network benefits are needed for knowledge combination and success of that knowledge combination. we need both short access to diverse knowledge and also cohesive networks, which increases the absorptive capacity of those cohesive parts that must face with diverse knowledge. If they face diverse knowledge, their cohesion will help them to understand different knowledge and to process them in their everyday work. So we expect that medium small wordness is ideal for creative outcomes, similarly to what Uzi and Spiro documented before in the case of creative industry. So therefore we have two hypotheses within hypothesis one. We hypothesize that small wordness of co-inventor networks is positively related to proportional atypical patterns in the region, versus the quadratic term is negatively related to that proportion. Okay, so then what else can we do with such networks? So starting from the classic regional development literature, in which the learning in the city is assumed to be influenced by industry structure, and the two pioneers and heroes in that literature that is still an ongoing debate, I believe, is that specialization matters because in an industry structure, because that helps incremental innovation and productivity, versus diversity is important because it helps radical innovation, radical combination, which can lead to employment growth. And I believe that that literature is now still progressing and was very much influenced by some methodological developments. Here I take the example of Cesar Hidalgo, who and others in evolutionary economic geography, who proposed ways to measure how much diverse knowledge is related to one another by measuring similarity relatedness across several objects. So here we use these conceptual frameworks and methodologies to understand the role of technologies and technological specializations in inventor collaboration networks, because we still need to better understand how diversity versus specialization increases and is helped by collaboration networks. So the problem here, and the literature here that we can contribute and refer to, is that probably it's, although we think that radical novelty needs diversity, we also believe that the specialization can facilitate innovation by the critical mass that it generates, because that critical mass increases the absorptive capacity to work with diverse knowledge in case there are some knowledge transfer mechanisms at play between these diverse knowledge pieces. So for example, I like this one, which is about the Boston biotechnology industry that had two background technologies basically at present around MIT, which was engineering and biology. And we know from the seminal paper of Powell and others in '96 is that the geographical proximity, of course, so that these two industries concentrated around MIT, and then that generated the opportunity that these individuals, these specialists, could meet and socialize with one another, and these social relationships help them to mix biology with engineering technologies, which led to the biotechnology industry, which is booming now, and Boston is one of the global hubs in that industry. So I think we still have a lot of opportunity to include those insights into measurement. One of the problems is that the role of technologies and the role of knowledge is related to network dynamics. So, of course, similar specialization in knowledge increases link probability, which we know that was thought to lead to regional lock-in because it was claimed and asked whether that too much specialization, too much cohesion in the network, how can we diversify from such situations and not to get locked into certain technologies. So interregional links, the thought to be one way to get rid of too much specialization and get some diversity. But we have also seen that local variation might matter because these entrepreneurs, inventors, they might go and reach out to different knowledge spaces intentionally, right? So they might see the benefits of knowledge combinations, and they might act intentionally. So one of the problems that we had to get rid of is the impact of knowledge and network on network dynamics, which is very difficult to disentangle. So for that, we used a solution that is very widespread in network science, in which basically, which is a network, it's community detection, the community detection technology and algorithms, in which one can identify cohesive segments of networks without using information on in our case, knowledge or previous experience, but only using information on the network structure itself. So if you do that and identify which are the cohesive segments, then by definition, we going to get those partitions of the network that are tightly connected within, but only loosely connected to other similar cohesive parts of the network. So then what is left outside of these communities are the bridges by definition. So and once this is done, we can measure the technological specialization of these isolated groups that we find on the network using only the network structure. So we did that and measured three qualities of local collaboration networks. The first one, after finding inventor communities, the first one was their specialization. So we could, of course, see the history of every inventor that participates in these communities, and then what we did was that we calculated the Hirschman-Herfindahl index of ICT classes that are present in each community, and then took the median level of that Hirschman-Herfindahl on the regional level. As you mentioned, we did several robustness checks. That was a first try to understand technological specialization in these regional co-inventor networks. Then what we can do is that we can also quantify the links across these identified units, right? So we can calculate, we can count how many links are present in this network that bridge one community to another. Then what we can also do is that we can measure the difference or the similarity of the technological portfolios that are in one community and in the other community. So we can just simply calculate how the overlap between these distributions of technological activity in these communities. Okay, so now the hypothesis, what do we expect? We expect that in case specialization of inventor communities increase, then this comes with a increasing scale and scope of knowledge in that domain in the cohesive network partition, which can support the combination of that knowledge that is present in that community with external knowledge. Okay, so we expect that the median level of technological specialization in this in the regional co-inventor networks will be positively correlated to typical patterns. We also expect that if connections increase across communities, that also helps atypical combination, because this is a new channel. This is a channel of channeling different communities, a channel of knowledge transfer between those partitions of the network that are only loosely connected to one another, which helps access to diversity. Finally, what we can still expect is that if these bridges across communities breach indeed difficult technologies, then we expect that this will lead to more atypical patterns in the future. So let's switch the results quickly. What we did after calculating these measures was that we estimated, and here it's a mistake. We estimated the share of atypical patterns in time period +1, so t+1 in the region. And this was about like, and I forgot to mention that. Sorry for that, but we had 5-year intervals across 30 years. So here T means a 5-year period, and then we estimate the share of atypical patterns in the next 5-year time intervals. Okay, so I'm confused. So then it's there. It's not a mistake. So we estimate that in a planar regression in which the next period is estimated by the previous period indicators, including small worldness, specialization, share of inter-community ties, and the similarity of connected communities, and a bunch of control variables, time and regional fixed effects, and of course error terms. So here we have a bunch of regional level controllers and a bunch of controllers that relate to the inventor networks themselves. So, but the control for just few to mention, average related density, which captures similarity across technological classes in the region, complexity, which refers to the indicator developed by Hidalgo enhancement, capturing complexity of economic activities. We also use that indicator. We control for the density of collaboration networks within region, the share of isolated inventors, which was claimed by Lobo and Strumsky to correlate with innovation activity, the number of communities, population, inter-regional ties, and many other indicators, and found consistently that the first hypothesis holds. So small worldness on the left side of its scale correlates positively with atypical combination in the region, but we do not find this reverse U shape. So basically, it's still what Fleming and others suggested, that as the network gets smaller and smaller, we see the increasing potential for atypical combinations, because probably information spreads quickly. There's a lot of support coming from the networks and the short access. What we also see, if we go to model 2, is that increasing specialization on the regional level in the communities is correlated with atypical combination, suggesting that indeed, as we can expect from the literature, if there is a growing critical mass in technologies in the collaboration network, then probably these partitions, these cohesive parts, can internalize external knowledge when they do novel combinations. We do not see, if we just include the share of inter-community ties in the model, we do not see a significant correlation. But if we control also for their similarity, then this coefficient turns significant, while similarity is negatively correlated to atypical combinations, suggesting that it indeed happens what we expected. So if these bridges across communities link this similar knowledge, then atypical combination is more likely. So we could verify 4 out of 5 hypotheses. We could not verify the 5th one, but I think it's still a cohesive story what we can tell, and this holds for atypical patents and not really for patenting in general, meaning that we still are consistent with previous literature, because previous literature said small wordness in itself is not beneficial for growth. It's path length that matters for growth. We found that small wordness is good for atypical patenting. We also find that if inventor communities are becoming specialized, that helps novel combinations, especially if different specializations are linked across the years. So we did a lot of robustness checks. First, we just did the community specialization calculation by measuring the mean and standard deviation of community specializations in these regional networks. It's still an aggregate measure. So there are some problems which I will talk about in a minute. We also looked into a model in which the lagged independent variable was included to capture dynamics. We found the same thing also in robustness 1, robustness 2. The results were holding. We checked other network variables, the one on associativity, to check some other ideas that are present in the literature. We normalized the community size instead of using the community number. We did different community detection techniques because during the division process, this community detection technology was criticized. So we looked into different algorithms which basically showed the same results, and we tried to do our best to include interregional collaboration within the networks of places, because that's still a problem, and then I will talk about that in a minute, that the network of places transformation, although it is a very useful tool to get rid of the automatic try-declosure in these networks, create additional problems which one has to carefully handle. Finally, we tried to include interaction terms of similarity of communities in the region, specialization of communities in the region, with the extent of which these communities are connected by collaboration. So that would provide us even stronger evidence that it's indeed these bridges across dissimilar or similar technology, across these specialized communities help novel combinations. We found no evidence for that, for these interaction terms, which is probably due to the regional application. So what future research could do probably is that zoom into smaller levels of observation. So now in this first paper, we looked into the regional scale, aggregated everything on the regional level, but of course, atypical patenting is not something that happens in the region. That's something that happens in companies, in collaboration or on the individual level. So probably what one can do is to zoom into companies, zoom into inventor communities, zoom into patents itself, and try to identify how the collaboration network can lead to novel combinations. For that, I think we need better understanding how cohesive segments and bridges indeed have such combinations. We still need to understand better the role of brokers, those inventors who make the bridging connections, so how they combine technologies across companies, regions, or technology specializations. And what is the ideal scale for inventor communities? That's still a question we need to answer. And what we can still do and what we should do to better understand what is happening is to probably to distinguish technologies by their complexity and life stages. But I think what is still important for us to understand how network dynamics induce combinations is network dynamics, basically. Network dynamics itself. And let me tell you one example that I love from the interdisciplinary literature, which is about tribes in East Borneo, in which in the paper, which is done by anthropologists and physicists, they look into network dynamics. The question is, how do these tribes improve the ingredients of the drugs that they do at home by trying these ingredients and learning from one another. So these tribes live far from each other in different villages, but eventually, and on a weekly or monthly basis, they meet in the central village where they have the market. Okay. So then they learn from each other. They learn what are the good combinations of ingredients. They go home, learn how these work, probably with trial and error, probably include some other ingredients. And again, they meet in a month in the central place in the market and share knowledge. So I think this type of causation in the network is very essential to consider if we talk about innovation in networks, because both specialization and a mixing is needed in such networks. The question is, how much specialization do we have? How easy it is to mix with other technologies, and how much the bridges that can contribute to this thing. And of course, timing, as I said, is very important. Then let me finish with
yes, because I was asking you to go to conclusions.
Okay, so conclusions is the final one. So I'm now just let me do this final plot, which is about diffusion. So still, I think there's a lot to do on network diffusion, in which we have models coming from network science, which could help us to understand how technologies and innovation is going from one part of the network to the other part of the network, in which links are very important, but also the cohesive part is very important. So we could understand better how the different types of knowledge is spreading from one part to the other part, what organizations and firms have to do with that, and how specialization and relatedness contributes to that. So the conclusion here, what we have in this paper is that the small word co-inventor collaborations help radical innovation, and the specialization into technologies is another factor that strongly predicts future levels of atypical combinations, in which and also like the bridging collaborations across different technologies that can help atypical combination. So what we have as a final message in this paper is in regional innovation, it's not diversity per se. It's the presence of multiple diversely specialized inventor communities that need the interlinks that can favor radical innovation in the regional economies. So with that, I would like to thank your attention. If you're interested in the paper, please have a look. It's out in the research policy, and of course, I'm waiting for comments, and thank you for this opportunity.
So thank you, Balázs, for this excellent and very complete presentation, I give straight the word to Lorenzo
Yeah.
for your comments.
Thanks a lot. So I'm going to share my, hopefully you are seeing the PDF. So thanks a lot, Balázs. It's a very interesting presentation, very interesting paper. Quite dense, complex, I have to say. And I'm sharing your approach, your view. Definitely sympathetic with that. I like very much your results. So I'm not going to comment too much about the results and your interpretation. I'm going to focus more on some methodological issue. Okay, so it's something that that is new for me. You use a lot of different techniques in a very correct way, but there is something about the network of plays that for me raises some question and some issue as well. And question and issue that I have no answer about that, and I have no a clear opinion either. So first of all, I have tried to explain myself what are network of plays, okay? Because you are doing something that is not traditional, or if you want, it's not typical. Maybe it's going to work. Okay. So let me. Okay. Moreover, maybe my discussion is a bit technical, and so I'm sorry about that. And for sure, my slides are not nice like yours. So again, I'm really sorry. So let's see here what I have. So I draw very simple network. The first column is the information about the patent, that are the numbers 1 and 2, and A and B and C and D are the inventors. So patent 1 has been the results of a collaboration between inventor A and inventor B. The second column is representing a two-mode network, what you have shown before in your presentation. When you take the example from the figure from Breschi and Lissoni, there was also reporting organization. I make simple here, and just there are A, B, C, and D, the inventor, 1, 2, the one-mode network is more or less what everyone is using as a simplification. And in the one-mode network, you have that nodes are inventors, and the link is the fact that two inventors has collaborated in a patent. And then there is the network of plays. That is what you use, the methodology that you use, where nodes are an aggregation of inventors, if I get well, where inventors are belonging to the same node if they are structural equivalent. Structural equivalent means here if they have the same set of links, direct links.
Yeah.
Right, no?
Yes.
So things now, we have the first two patents. We have this very simple, where one mode network and network of plays are exactly the same. Then we had another patent that now is patent number 3, where B and C are participating. And again, we have the same structure, Z. Now, if Y is not moving, okay. Now, we had the other two patents, 4 and 5. 4 is a collaboration patent between A and C, and 5, B and D. So I'm going to add in one mode network the two links. The effect of these two new links is going to change the nature, the identity, if you want, of the nodes. Now you have two nodes. The first one is of two inventors, A and D, and the second one, B and C. And they have just one link. Finally, if we had the final patents with the missing link between A and D, we are going to have a click between our 4 inventors in one mode network, and in the network of plays, we have just one point, an isolated that is representing the 4 inventors. Is it right?
Yes.
Okay. So of course, and I agree with you, since you are interested in looking at the overall structure of the regional networks in terms of small worldness, you need to avoid the problem of one mode network that, let's say, in a deterministic, automatic way, is going to give you a very high clustering. That is, so that's it. I like very much, but for me, that is a huge change. It's a huge change that make sometimes difficult to compare your results with previous literature. And so first, I would like that you are going to produce more paper using this methodology in order to see if the results that we got before, thanks to the one mode representation, are still there. Okay, I will make an example later on about density. That's for example. So that is what, just to be sure that I have understood. So then you say, okay, we made this, but at the very end, there is a not huge change in terms of the two representation, in terms of number of nodes and number of edge. There is a quite high correlation between the two distributions. Yes, that is true. I'm not made so much optimistic. I see that for very few value can be quite a huge difference. And then we will see why this is important. All of these, not to say that you are not doing the right choice. It's just to say, I'm not sure that it's so easy to compare the results that you get with previous literature. That is the point. Otherwise, I agree with you, is what you have to do in order to avoid high clustering. So now, maybe it was not clear. What is asking for me a bit, was a bit problematic is your measure of small worldness. So I raised the issue, I don't know the answer. So the point is that the equation 4, that is a synthetic measure of small worldness that is capturing both mean, the average distance and the clustering, is going to give just one value. And usually is something, as you say, that is between -1 and 1, where 0 is the small world. And in order to use this in a regression, what you are doing is apply equation 5, where you have that 1 is small worldness and 0 is the opposite. The issue is, for me, is that the opposite are two very different things. Because as you have defined the small worldness, 0 can be random, but also regular or lattice distribution. You see what I mean? So the issue is that the small world is characterized by high clustering and short average distance, while 0 can be a structure where you have a very high clustering, but a very long average distance. But at the same time, 0 is also the structure that can be very low, the opposite. So very low clustering and very short average distance. Okay, so I don't know, but maybe you are not able to get the reverse U-shape for that. That's my intuition, but I'm not able to go more in this direction. Okay, so that is for me one of the problematic points of your results. Coming back, so sorry, maybe coming back to this. Okay, I don't know what. Do you see still the diaporama? Yes. Okay.
Yeah.
Here on the left, the one mode network usually used. On the right, your network of place. On the left, we have a clique, a very dense network. On the right, we have an isolated one. Okay. What does it mean? That if you want to compare your results with a previous one that are using the one-mode network representation, for example, relative to density, is a bit a tricky issue, because in your isolate, there is also hidden, let's say, many density and a lot of density in the one-mode network. I don't know if I'm able to explain.
Yeah, of course. Yeah.
And so when you see your regression, of course, density is not significant, but you see isolate is positive, density in specification 8 is negative, but when you put the two together, density change the sign. Still not significant, so it means that once you control for isolate, so the hidden density, the sign of your density is changing. So of course, that result is completely marginal to what you have in your paper, your conclusion, so on. But for me, it's telling you, be careful, that is very difficult to compare previous literature with what you have done. So I conclude with an invitation, since it's you that is, and Dieter and the other that are going to work, not me, so it's very easy to make this invitation. It will be nice to have a paper where you are replicate previous known results with the same data, but with your methodology, in order to see how much things are changing. Okay, so that is a York for you. That's, so for me, it's easy to say that. And in this way, I conclude, and I don't know, I open the discussion, I guess, but that is going to tell us how does it work. Okay.
Yeah, thank you, Lorenzo. I don't think we should spend a lot of time on these very technical issues. But Balázs, maybe you would say 2 words, but please 2 minutes, because I want to leave space for comments.
Yeah, I absolutely agree. 2 words is thank you very much. Absolutely right. So I really like your example on network dynamics. So probably we make very, and usually I think the decisions we have to make in constructing collaboration networks from co-occurrence data is very tricky, and one has to make very big assumptions. And ours, the one that we made, the network of places transformation, is already a big one, which creates additional problems as you measured. Some circumstances decrease the magnitude of the problem, some increase. So the networks of places are usually small. So 2 or 3 inventors are in there. And of course, we have a big enough time window so that probably the time window, big enough but small enough time window, so the collaboration in patents within 5 years. So the assumption is that if these collaborations happen in the order that you just proposed in the first few slides within 5 years, then we can assume that the work has been going on already, the collaboration was there. So probably these inventors, even if they produce the patents sequentially, they still had the same set of collaborators. So basically that's the assumption. However, I completely agree that this is a big step, and I like very much your invitation to the next paper. So that's something we should do. Actually, when during the referee revision process, it was the fifth round that we were asked to do this repetition, and then it was too late for this paper. But I think you're absolutely right. So that's something we should do. Thank you so much, Lorenzo. Very, very, very helpful.
Thank you. I would like to open the floor for questions. I see Thomas appearing.
Yeah, if I may, I didn't found the hand raising too. Sorry. Benedetto, I think you should make a note that RISIS is not only a good infrastructure, but also now has an active contribution to knowledge production, bringing together new co-authors. So this,
Yes.
this is really something we should
That's
make
the
a note
goal
of.
of
So
these
that's wonderful.
seminars.
Yeah. Thanks, Balázs, also for the wonderful presentation. I go with Lorenzo, very sophisticated methodologically and so many issues to discuss I will not raise now. I want to bring it more to a general level. Again, maybe can you reflect a little bit again why or you think that your dependent variable is a good proxy for radicalness? I'm a bit puzzled about it, because you could say, okay, if you have a lot of atypical patents in the regions, it could also be the case that the technology goes down, and then the technology is still existing in the region is atypical because the technology is not relevant anymore. But with radicalness, we want to measure somehow more the degree of innovation, right? The degree of knowledge increase, which I think by some authors is done by patent citations and so on. Maybe you can reflect a little bit again in that respect, why you think this is still a valid measure for it. And my second comment, you have complexity as well as an independent variable. And of course, I mean, maybe I'm getting it wrong, but the atypical patents is somehow also very much related to the complexity notion, because complexity is a combination of diversification and ubiquity, and of course ubiquity is somehow strongly related to atypical patents. Maybe you could also reflect a little bit on that potential endogeneity issue you have.
Yeah, thank you so much. Again, that's something I cannot disagree with. So I completely agree that the atypicality is something that is very weak to measure radicalness. So I apologize if I put it wrongly. Sometimes I need another word than atypical, which is or novel. Or sometimes I say radical, but I completely agree that we cannot measure radicalness in this respect. So what we measure basically is like whether that combination existed before or not. So this has problems, and now people raise really some criticism about that measure. So this one was atypicality was something offered to measure novel combination in science, but now people increasingly show that basically it is still not free from size. So basically size produces that, which is a problem. So I think we need to go beyond that. So definitely if like the core of my message is like the network dynamics, but we want to use that for describing technological process, probably we need a new measure and not just atypicality. And there's a lot more out there on radical innovation. You know better than me. But I take the note. So this is something that we should do in future research. Then I'm not sure about the endogeneity question. So what type of endogeneity you would
yeah, because my thinking was that, can you hear me? Yeah. My thinking was that the atypical measure, so the atypical patterns in a region comes quite close to one very important part of the complexity measure that you used, Hidalgo, which is ubiquity. This is then intermingled with diversification, of course, but it's I would assume that many of these atypical regions you find are also those that will get a high complexity score. Let's put it like that. I mean, did you check the correlation between between the dependent variable and complexity?
I'm pretty sure we did. It should be somewhere in the very long appendix. I cannot remember now. If you want, I can check it up.
No, it's just for you, maybe you to think about it.
Yeah, I agree. So like, yeah, this is not a perfect. I cannot say that this measure is a perfect measure that is on the left side. There is good motivation to look at it, because as I said, we found that the previous research found that this is a concentrated measure, which can tell us a little bit about the need of atypicality, the need for diversity. So I cannot really see any more reason why big cities have more atypical patterns than small regions. And I think it's not might be linked to complexity, but I think it more relates and to the diversity side of complexity and not the ubiquity side of complexity. I'm not sure about that, so I just make a note for myself. But thanks a lot for the question.
No, thank you. Yeah.
Thank you. Are there other questions?
I have a short question.
Yes.
Yeah, so I'm just waiting for Georg to mute his speaker so we don't have interference. Yeah, thanks for this presentation, very interesting. I have a question. So atypical combinations are somehow the negative of a typical combination, I take it, or the inverse. So if you have a lot of atypical, then you have less typical combination, I guess. So does that then mean you find a positive effect of specialization on atypical combinations? So does that mean that you would get a negative effect of specialization on typical combinations? And how does that work with the expectation that would go the other way around? Or is this not a good conclusion from that?
So actually, thanks, Nico. Thanks for the question. So let me go back. If I can share the screen again. So I have an easy answer for that. So what we did here is that we also looked at total pattern growth rate. And here specialization has a bigger coefficient. So it's like completely, you're right. So if the pattern is atypical, it cannot be typical. So given the size or the number of patterns in the region, if we have to distribute them, it's either atypical or atypical, it cannot be both. But still, if we have total patterns, it's still specialization still matter. What doesn't matter is connections. At least it's not significant, and also not significant is small burdens. Otherwise, similarity matters, which I'm not. Yeah, I don't have a clear story why it's still important. Probably we need different knowledge for all types of patterns, but bridge is not that much. So yeah. But thanks for the question.
Thank you. I think we are now moving towards the end, but I just have a small curiosity, because you could make exactly the same argument for science instead of technology. Do you know whether the kind of techniques you are using were used also for science studies? Because I found, as a sociologist of science, I would have the same argument, that it's just not just recombining, but to create novelty in science, you need strong two areas which are clearly specialized, and then you have something to combine, and not just a very sparse network. Do you know some uses of these techniques?
Not exactly. Thanks for the question. Not exactly this technique that we are doing, but it's a very basic technique in network science that we do. Okay. So network science tend to think that community detection is kind of not exact, has a lot of problems. So they even try to extend now, and there's this emerging field of science, which do a lot of similar stuff using scientific publication data. So now a lot of questions are about the dynamics of groups and the dynamics of collaborations, because then this data is much richer than what we have in patents. Indeed, there's a lot that is happening also on diffusion in networks that I had on my last slide, because I think that one very nice insight that we might use doing networks in innovation studies is that there are models in which diffusion of ideas can be investigated. In science, in scientific publications, we have co-author networks, we have citation networks, we might use text mining techniques to understand what is the core idea in some papers, and then we might be able to model how these ideas are combined in scientific collaboration. So I think what you have in mind is absolutely relevant. So thank you.
Okay, thank you. If there are no other questions, I think this was a fascinating workshop. And for me, as a more scholar in science and higher education, an opening of a world, and we see there are always similarities. This was the last seminar of this year's series, but this is not the end of the series. The seminars will restart in September. We already have some bookings for the new seminars. And if some of the presents would like to submit to present, please email me and we will agree on the timeline. I found the format very helpful for learning, but also for presenters, as you've seen, to get useful feedbacks for future research, which is what we want. So thank you to Balázs for presenting, to Lorenzo for his very to-the-point discussion. Thank you to Georg and to Rita for the organization, and have a nice afternoon. Bye-bye.
Thank you so
Bye.
much. Bye.
Thank you. Bye-bye.
Goodbye.